So we're talking about power supplies. This is the basic makeup of what we refer to as a linear power supply. We have two categories of power supplies. Now, normally we use the term power supplies. These are DC power supplies, which are basically AC to DC converters. And what's the advantage of AC? What's the major advantage of AC? We can step it up for transmission and step it down for safety, right? Y'all understand that? We can use it very efficient. It's not as efficient as DC. If we could get DC up to 750,000 volts, that would be more efficient than AC. Because for y'all that's had AC, we have two units in AC that we call inductance and capacitance, which create phase shifts in the circuit. AC don't have that. So when we talk about opposition in the AC circuit, we have resistance, we have we have two types. We have resistance and we have impedance. In the DC circuit, we've only got resistance to worry about. You understand that? But the problem is DC is real hard to step up for transmission and step down for safety. So if we could get 750,000 volts of DC, that would be a heck of a lot more efficient than 750,000 volts of AC. But it would be extremely hard to get that much DC voltage, right? You understand that? Now, they are doing some of that with some of the solid state devices we have. They're doing some high voltage DC. They are. I think one of the power things that run under the English channel is high voltage DC. So, but power supplies, we have two basic means of DC power supplies or types. We have what we call a linear power supply, which is what we're going to deal with, and it's easy to design and it's easy to fix. So if you're going to build one, this would be the guy you would be. And plus, linear power supplies can have the ability to produce the most power. The biggest problem they have is it does not do it extremely efficiently. So it has a lot of power loss inside the power supply itself. Efficiency would be what when you come over here and you measure the power on the input, and so the efficiency would be power in over power out, right? You understand? And what we're shooting for, and then we'd multiply that by 100, and that would give us our efficiency. And what we would find out is the input power is always going to be less than the output power, and that's true, right? Power consumed or energy consumed will always be less. Energy produced would be less than energy consumed. Sorry. Yeah. So input energy is always more than output energy, unfortunately. So anybody tells you they have made a machine that don't require, you can look at videos on YouTube all the time and they'll have these people, they'll hook a generator up to a motor, and then they'll run them, and they'll go over there and unplug the motor, and it appears like the generator is producing enough power to run the motor. You need to just turn those things off right off the bat. Those are totally safe. So anyway, we had a guy that came in here, and they had big DC forklift. It had these big old batteries. Said, you know what I'm gonna do, Rich? He says, I'm gonna put a generator on the wheel, and that way, when they're running forklift around the shop, they charge back. And I said, no, the batteries are running down fast. He never did it, but I don't think I ever convinced him. Yeah, so it would take more energy to run the batteries than the voltage you get out of them. So it actually. Then you'd add that to the energy of running the tractor, and you'd never be able to start. So this is the basic makeup of a linear power supply. The other power supply, is what we call a switch mode power supply. Some people just call it a switching power supply. And we won't build one, but I'll hook up a simulation. No, it's not even a simulation. I'll hook up a section on it that's really, really neat up here and show y'all how that thing works. It's really neat, and you can see. But it's real hard to design. But this is the basic makeup of a linear power supply. We start off with this is this is pretty normal, but what we want to do is put the most prevalent where we come over here and right before the rectifier, we're going to put a transformer. I'm not saying you won't find linear power supplies without transformers, but probably over 90% of them have a transformer. And what can we do with the transformer? What's the function of the transformer? Step up or step down, but in power supplies, it's to set the voltage to the load. So if I'm going to have a power supply, that transformer is going to establish the voltage that I take from AC and convert to DC. And so sizing that is very, very important. Then we feed this into rectifiers, and what's the function of the rectifiers? So it converts AC into something we call a pulsating DC. And this is where we're going to start out at. We're going to have a transformer. We'll let y'all use the transformer on the trainer, but I'll show y'all the whole setup here. I've got mine. I'll use the actual transformer, so I'm not going to use the trainer up here. And then we'll look at it on the oscilloscope, and we can see that. The function of the filters is to convert pulsating DC into unregulated DC. Rich. Now, what we mean by unregulated DC, if this input voltage varies, the voltage would vary, or if the load varies. So that means if we require more current, the output would go down. If we require less current, the output would go up. And then the regulator converts unregulated DC into regulated DC. So what we mean by regulated is over its set range, it maintains a constant. Of course, it's not going to be exactly constant. It's going to be maintain an almost constant output, even though the input voltage is varying and the output loads are varying. And this is regulated DC. And of course, that's what we want, right? Well, that depends. It depends what determines what type of DC we need. Somebody take a guess. I mean, function of the power supply, it's got one function. It's to apply power to a load somewhere, right? So what determines what we do is the requirements of the load. If I can, I'll stop right here. If I can, I'll stop right there. And if I can, then of course I'll go all the way. So it depends on the load. What does the load need? And what we want to do is we want to make as minimum as we possibly can to run the load, right? You understand? So it'd be silly for me to go all this route right here and run a motor, a DC motor. A DC motor don't care about it. It loves it runs just as well on pulsating DC as it does regulated DC. But if I was going to run a piece of electronic equipment don't like it. It likes nice regulated DC. So if I was going to run this on my car stereo, I wouldn't use pulsating DC, right? I'd have regulated DC. So where do we cut this off depends on the load. So what we're doing right now is we are cutting it off right here. And our rectifier we got one rectifier. It means, so what we're going to do is we're going to convert that from the power source. Of course, we got our transformer in here. And we're going to convert this into what we call half wave. So this is a half wave rectifier. And guys, I mean, this is about as simple as you can get. So here's the circuit. Right here. Here's my diode, here's my load, and here's my transformer. Now the transformer that we have is rated 110 volts and 12.6 volts at 1 amp. Now that's what it's rated at. Now it's going to be extremely highly unlikely that we get exactly that, and so when we design the power supply, we compensate for this kind of stuff. But odds are, since we're only putting an extremely low load on this thing, then odds are we're probably going to get out more than 12.6 volts. That 12.6 volts is saying, okay, you'll get 12.6 volts if you're putting 110 volts on the primary, and you're loading the transformer to 1 amp. And what's the odds of me putting 110 volts on the primary? Exactly. What's the odds? What's the odds of having a 100 ohm resistor, 5% 100 ohm resistor that's exactly 100 ohms? Pretty high, right? You understand that? I mean, pretty low. So, but when we calculate it, we'll calculate it for what the transformer says it is. So when we calculate it, we'll use 12.6 volts. And by the way, this is a center tap transformer. And what does that mean? What's center tap transformer? Huh? Yeah, because what it means is it's got 3 windings on the output. So I'm just going to draw the secondary side. And then we have a tap coming in directly into the center. We got 3 places we can get voltage. What I'm going to do is we're going to use the entire transformer. So that means we would get the entire 12.6 volts. And then right now I'm putting my diode in this direction right here. And then my resistor is a red. What's that? Red. It's a red. What does that mean? Probably 2%. Okay, so what's red? What's red? Red's not 3. What's red? Guys, what's red? So y'all don't know what red is? Christmas. It would be red if it was red, red, black, but it's red. Yeah, is that what you said first? 2.2K. Y'all not impressing me. So every test y'all have, you're going to have color code questions on it. Guaranteed. And if you come and ask me for a resistor during lab, you need to know what? Color code. Okay, so calculate this for me. So what voltage should I get out? So we're using 12.6 volts, even odds are that's not what it is, right? You understand, but it's going to be close enough. And this is what you do when you calculate according to the values that you're using. It's a 12.6 volt center tap transformer. I'm using the whole transformer. So what would my output be? Oh, did you say it would be 6? Did you say 6 volts? Did you say 6 volts because you calculated, or did you say 6 volts because it's halfway? So what's the first thing we need to do, guys? Tell me number 1. What's the first thing we need to do? We worked these last class. Undoubtedly, everybody slept through that class. So what's the number one thing we need to do? What's that? Find VP. Great. So VP would be equal to what? 12.6. Are we going to multiply by 0.707 or are we going to divide by 0.707? Okay. So we're calculating for VP. VP is big. If I divide by a fraction, I get something bigger than I start off with. If I multiply by a fraction, I get something less than what I start with. This is the peak, right? You understand? So what are we going to do? Are we going to divide by it or are we going to multiply? Huh? I'm listening. We're going to divide by it. Great. So V peak has got to be greater than RMS. RMS is an effective voltage. RMS is basically an average. So that'd be me asking me about what's your average salary for the year and what's the biggest paycheck you got. So the biggest paycheck you got would be V peak, right? You understand? And VRMS we call it the effective voltage, but it's an average using RMS means of getting that. So what do we got? What's that? Point. We're rounding to 1 decimal point. 18 point. Okay, 17.8. So we use 17.8. Sorry. So we're rounded to 1 decimal point in this class. 17.8 volts. And you should put P out there because this is not RMS, just to make sure we understand it. So 17.8 volts P. What's the next thing I'm supposed to do? We don't need VP. We're through with that. I mean, VP, well, all we need to calculate the output voltage is we need to calculate V peak out. Now, V peak out is what we're going to do is we're going to subtract the diode drop from this. And we're going to use second approximation, which means we're going to use 0.7 of a volt, because I didn't tell you what that was. So I'm going to say V peak out is equal to 17.8 minus, and what do we use for silicon? 0.7, right? So V peak out would be equal to 17.1 volts peak. And we'll put 2 scope probes on here. Well, it's going to be hard to do. Now we can calculate DC, volts DC. What's this? Good. 17.1 divided by 3.14, which is what we're going to use for pi. So what should we have? What's that? 5.4 volts. So this is what we calculate just using the ratings of the transformer and using 0.7 of a volt for a second approximation. Y'all understand that? Okay. So here's the circuit. Here's my scope probe. And somehow my scope turned off. No, it's on. It's just blank. Where's my scope at? We'll start off. Let's look at what's going on here. So here's I'm going to use 2 scope probes so we can actually see the AC coming in and the DC coming out. So that's the AC. So here's our the yellow signal. Y'all can pick this up. Is the AC coming in? Channel the blue is DC coming out. And look, the output peak is slightly less than the input peak. Why is that? Yeah, when I look at this, you can see this. Here's the input peak, which is yellow. Here's the output peak, which is blue. Can y'all see it's slightly less? Why is the output peak slightly less than the input? What did we subtract from it to get V peak out? We subtracted the diode drop. So you can literally see why we do that, right? Because you can see the diode drop right there. So there's a diode drop right there. I got it on 10 volts per division, so it's hard to see 7/10 of a volt. What I'm going to do now is I'm going to get rid of, I'm not going to get rid of channel 1. I'm going to move channel 1 over to the output. And so here's our DC. By the way, what's going on? Anybody needs the scope? What's going on? No, why is it jumping all over the place like that? Well, it's still, how can I measure this if it jumps all over the place? What's wrong? Huh? Not the scale, not the time. The problem would be here is that you're sitting back here, everybody in this classroom, I said, okay, y'all start opening and closing on Friday. And I'm doing things up here. How many of y'all would see the same thing? How many of y'all would be in sync with what I'm doing? None of it. Unless I could give you a signal when to open your eyes and not when to open your eyes. So this scope is hooked up to a waveform. It has no idea of the frequency. It has no idea of the time. All it's doing is displaying what it sees. Right? You understand? But the scope is not synchronized with the signal itself. Now, if I synchronize it, I'm going to make it display relative to something on that waveform, and we call it trigger. So the scope is not triggered. The scope is not synchronized with the waveform. So one of our main measured things over here on this scope right here is over here on this side right here is called trigger. And notice when I move it, I get a white line. As soon as I get that white line into that waveform, what did the waveform do? Stop, because now my scope is synchronized with a voltage spot on that waveform. So what we do is we set a voltage spot on that waveform, and now every time it sees that voltage, it does what? It displays. So now not only do we set up a voltage, but we also set up a slope. So what I'm doing when I look at my trigger menu, so I've told my scope to synchronize on what channel? Channel 1. I'm telling it to look for a watt, an edge, and I'm telling it to look for a rising edge. Y'all can't see the arrow. Now here's the trigger point right here, and what you need to look at is notice that white line is right where that thing crosses this guy right here. Right there. See it? So now we got our scope synchronized with the signal, so the signal appears to be the same. But why does it appear to be the same? It's because this is a repetitive waveform. And if you got a repetitive waveform and you start it at the same time, thank goodness you know motion pictures. Y'all know motion pictures are just a series of pictures. And if the picture never changes, it looks like it's what? It's stationary. So even when they throw the sign up on your TV and it stays up there for 5 minutes, it's a different picture. It's just doing it, and it stays. Every picture is exactly the same thing. Fine. And the TV is synchronized with the picture, by the way. So when they transmit video like that, your TV has no idea when to do the picture. So what do? Well, they send what we call sync pulses with the video. So when I start a picture, they send a sync pulse, and then your TV picks up the sync pulse, and now you're what? Now your sync pulse is in sync with the what? With it being transmitted, with the transmitted. Because how in the world could your TV be synchronized? And sometimes we see that sometimes when, I don't know if you've ever been in a movie and all of a sudden the thing starts rolling because the projector is out of sync with the video. In the old days when they used film. In the old days when they used film, they had all these individual start running that thing, and you have little adjustments to adjust it to get it in sync. Of course, now most of them use DVDs just like we use. Yeah, they download now. Used to you could tell when the new films come in because that big old truck would pull up and they'd come out and they'd have this big old car and they'd have all them big old reels of film. But now they download the movies just like we did, except they get access to them a lot sooner than we do. Yeah, they can get in there. So we're triggering on the rising edge, right? I'm sorry, triggering on the rising edge, channel 1 and edge triggered. Notice if I come over and take the little white line and put it up here, now it never sees that voltage and the thing will go out of trigger. Because the voltage is not getting that wide. It's not getting that high. The edge does not get up to where I'm telling to sync the scope at. A while ago what was happening, it was down here right at the 0 point. And it couldn't see the edge. That's what was going on a while ago. Okay, so now so if you're looking at a scope and you see it jumping all around like that, then it just means you need to set the trigger, right? Make sure it's set on the right channel. So that means a lot of times we'll have it set to trigger off channel 1, and we put our signal on channel 2 and turn channel 1 off. Well, if you turn channel 1 off, then that's what you're triggering. So there it is, guys. There's a DC. Ain't that neat? So the input looks like this. So AC in, DC out. And only thing that's between the AC in and the DC out is this little guy right here, this little diode. Now we'll measure it with our meter. We calculated 5.4. So where do I measure it at? Well, if I measure, let me put my, I gotta make me a profit. So if I come over here and measure across the transformer, oh my goodness, it measures 0. How can it be 0? It can't be 0 because we got an output, right? So why is it measuring 0? Huh? Well, that's obvious. You're right, Scott. But it's set on DC. So I got my meter on DC. And so it's giving me the DC average of a cycle. What's the DC average of a cycle? 0. We'll see how many got. This is a small class, and it's on the first test, and somebody's going to mess that in this class. I've never taught a class where somebody don't do that right. And why we really make sure you understand that is because this has got people hurt. They go up there and they measure, they think a circuit don't have power on it, and they go over and measure, they measure 0, and then they stick their hand in there. And they had their meter on what? They had the meter on DC when they was measuring AC. Now luckily DC, if you got it on AC, it's going to show you something, but it's going to be wrong. But if you got your meter on DC and you're measuring AC, it's going to show you 0, unless there's some garbage out there. So here's a cross-arm resistor, and it's measuring 5.9 volts. Now why is it measuring so much higher? So it's not, my good gracious, just by taking, and don't think, and this is why I asked you that a while ago, Courtney, you just divide it by 2. It just so happens that this worked out to be about half of 12.6 volts. It just happened to be that, right? Y'all understand that? But if we look at the actual AC coming in, so I'm gonna put my meter on AC. I'll try to. No, this meter you don't do that. This meter you have to switch. I don't like this. So the actual AC we got coming in is 14.6 volts. So since we got 14 point, why is it high? Well, it's high because we're not putting 110 volts into the transformer. And it's high because we're not loading the transformer with 1 amp. How much current are we loading the transformer with? Got 5.9 volts, right? got a 2.2 k ohm resistor. What's the current flow in the circuit? Or the calculated current flow? We're calculating current for 2.68, about 2.7 milliamps. We can check that though. So what I'm going to do, by the way, you don't wire and unwire circuits while they're operational. But this is you'll understand, this is, we only got 5 volts out there, and that won't hurt. The only thing we do is hurt the circuit. It can't hurt us, right? So what do I need to measure current? I'm going to come up here and break one of the leads. And then I'm going to put my meter on current. We're measuring AC current because we're getting it out of the transformer, but it's all in series. Let me set my meter milliamps. And what do we calculate? Over 2, right? And then we got it on AC, so I'm going to come up here, put my meter in series. And it's not measuring nothing. What do you think's wrong? Make sure I got it on AC. What do you think's wrong? Okay, y'all are experts here. What do y'all think's wrong? We don't have any current. We know we do have. We're supposed to have current. When I come up here and hook it up directly to the diode, it comes up and does that. Now I'm going to hook it through my meter. And I see that. Well, what's going on? What do you think's going on? Huh? Well, the meter, when we got it on amps, the meter's supposed to have no resistance at all, just very little. It does have resistance. Meter set on meter set on amps, and it's set on the 20 milliamp scale, and it's on AC. That's a good point too. That could be wrong. That could be right. So if I had it on DC amps, it's going to show 0, right? You understand that? Because I'm in an AC circuit. So what's wrong? So see here, I know this instantly. Or say, you're the teacher, right? The fuse is blown in the meter. Somebody blew the fuse in my meter. Since we're measuring current, and we could definitely damage the meter, the amp, right, Corey? The amps are fused. So somehow the fuse is blown in this meter. And it's the low current fuse too. It's got a high current fuse, and it's got a low current fuse. The high current fuse is 100 milliamps, so that's not much to blow a fuse, right? So somebody's blown the fuse in my meter. And I think this meter needs a new battery. Let's see what it does. So milliamps, common. And we'll turn it on. Put it on milliamps AC. Turn it on. And we'll see if this measures okay. Now it's measured 0 too. That's the problem with putting out meters that everybody uses, right? Huh? Yeah. Well, no, I don't. Were yours measured milliamps? Oh, you got a lot of range. So amps AC is telling us we need to do our readings.
So what did we calculate? So let's put it back on the meter. Y'all see Scott's meter? We calculated 2 point something milliamps. And so we got 2.1. Now why is it probably low? Well, it's probably low because it's not exactly a 2.2 k ohm resistor, right? So we measured 2. So that looks real good, guys. The meter we had at US Steel, the ohm scale wouldn't work if you used the plug. I forgot. I think it was a triplet. So before we ever measured current, we'd put it on ohms and touch it together. And if it measured infinity, it meant the fuse was blocked, which is pretty neat. What's auto V low Z? On the other side of auto V low Z. Yeah, but I don't know why you'd want to measure voltage with a low impedance. So there we go, guys. Now we're going to show y'all something. This is what we're working on. So right now we got the first part. This is probably one of the most popular devices used to filter because it's very cheap. We got 2 types of filters we'll use. In switching power supplies, they use inductors, and we'll talk about that. In linear power supplies, we use capacitors. And why do we use capacitors? Because they're very cheap. They do the job for us cheap. Inductors use copper. You use copper wire, and copper's not cheap, right? You understand that? So these electrolytic capacitors, to get a high capacitance, they're polarized. And by George, if you put one of these suckers in it backwards, you can blow it up. So what they do, this is what we call this a radial lead. A radial lead is one with the leads coming out one side, and then we have what we call an axial lead, which is a lead that comes out 2 sides. And it got the name. It's obvious how it got the name because it looks like an axle on a car. So what we do is this. I know it's not. I don't know if it's going to focus in or not. I'm trying to get it up there. Come on, put my hand behind it. That's the problem with autofocus. But you might see it. It's got the little minus sign right there, and then it's got an arrow pointing to this lead right here. So this is the minus, and this is the positive. Now, it's standard inside stuff that's polarized. That can you notice something else? One of the leads are shorter, and they only do this on the radial lead capacitors. They don't do this on the actual lead because it would be hard anyway. So if you got something if you pick up something and you see one of the leads is shorter, and that sucker's polarized, and it hadn't been cut. Problem is that sometimes they cut the leads off to make them the same length. So So I know this is a positive power supply. How do I know it's a positive power supply? How did I tell you to identify it? Don't do current tracing, just look at the diode. If the anode points toward the source, it's positive. If the cathode points toward the source, it's negative. So my anode is pointing toward the source, so this is a positive power supply. So I mean, the bottom of the resistor is negative in respect to the top of the resistor. Now what I'm going to do is I'm going to put my capacitor across the resistor out there. That's where we want the unregulated DC at, right? So I'm going to put my scope back out there. Oh, let me take, okay. And I'm going to take my scope and put it back out there. And then we're going to come over here and let me get rid of channel 2. I'm going to put channel 1 over here. And we'll turn channel 2 off. Okay, so there's my DC. I'm going to take my capacitor and just put it across the resistor. And look what happens. Oops. Oops. Let me put it on the camera. Okay. So that means this is 0 volts down here. It's pulsing up, right? Y'all see that? By the way, we're measuring DC, so by default means what it's going to use if you don't tell it something differently. So by default, when you turn your scope on, especially a digital scope, it's going to set your 0-volt reference right here. And that way it can show you it. So it's basically set up to measure AC signal. But the problem is, if I want to look at really see what's going on, then what we do is we turn the voltage per division down. Well, the problem is, as soon as I turn it down one notch, that worked. But if I wanted to look at it closer, it goes off the screen. So what I'm doing is I'm wasting a entire, let me reset my scope. You see what it's, look, you see what it's doing down at the bottom? That's not what's there, but you see what it's doing? Anybody use scope? What's going on? Yeah, what's going on is that we have two ways we can bring signals into an oscilloscope. And it's set up right. I don't know what it's doing. But it's set up right. Normally this is what we see when we have this set to AC coupling instead of direct coupling, which is DC. So I don't know what's going on. Some scope's having a problem. Well, let me show you what we're going to do. So what we usually do when we're measuring DC is we don't set it in the center. What we do is we go ahead and move it down here because it's not going to go negative anyway, right? And what that does is that gives us the ability to get a better resolution on our oscilloscope. So, okay? So what's this? I'm going to come over here and I'm going to put the capacitor across there. Negative polarized, right? So watch what happens as soon as I can get into the lead. My scopes are in place. Now, of course, it's snaking because we're out of our trigger range. That's pulsating DC. So it's going to 0 volts, 120 times a second. This is DC. But it's not regulated DC. Let me plug this in. That's DC. So it's not going to 0 anymore. But look, it's not, and if I come over here and I'm going to put a resistor in parallel, you should see the output voltage change. Can you see those ripples get bigger? Well, if the ripples get bigger, that means the output voltage actually drop down a little bit. So that what we mean, we call this unregulated DC because why? Because the output varies with load. It also would vary with my input. So it means if I took this right here and went over to building A and plugged it in, odds are we'd get a different voltage out of it. Because they're on a different transformer. So I think they have like 123 volts over there in building A for their AC. Here I think we have, I don't know, we'd have to look. So what we're going to do is we'll start here and then we'll filter it. So that's the filter. That's unfiltered. So we call this pulsating DC and we call this unregulated DC because it what? It varies with load. I'm trying to see if I got a smaller resistor. No. That's bigger than the one I got in. Okay, so we call this a half wave rectifier because we're only allowing one alternation to come through. Let's do one more thing before we go to the next circuit. Is what we're going to do is we're just going to turn. I'm going to take the capacitor out. I'm going to come up here and I'm just going to turn the diode around. I'm going to come up here. I'm going to turn the diode around. So here's the cathode right here, right? It's got the circle around it. I'm going to turn it around and I'm going to plug it back in. Now I got to shift my scope up. We'll redo the trigger. So here's 0 volts up here now. So what we got now, oops, is we've got negative DC. My scope pulled out the resistor. Can we power stuff with negative DC? That's the question. Where did y'all use negative DC at? Did y'all listen to y'all's radio? Okay. Is that audio going to your speakers? Is it DC or is it AC? That's what? AC. So if I didn't have AC, if I put DC on the speaker, it'd burn up. If you had AC, you'd understand the formula. You'd say X of L is equal to pi FL, and if you have 0 F, you have 0 X of L. But we don't ever put DC on speakers. You burn them up. So that means you're inside your stereo. Inside that stereo, there's plus and minus DC. So if I'm going to generate AC from a DC signal, then what two types of DC do we need? Well, so AC has to cross 0. Like that. So if I'm going to generate this, so if this is plus 10 and then this is minus 10, then that means somewhere, if I'm going to do this with a radio, or if I'm going to change the frequency, then somewhere I'm going to need plus 10 volts DC and then minus 10 volts DC. Now if I have that voltage available and it's DC, what advantage does DC have over AC? What advantage does DC have over AC? We talked about this last class. What advantage does DC have over AC? We can electronically control it. So by George, if I've got a plus DC available and I've got a minus DC available, then by George, I can control it to get an AC out of it. And if you look at this function generator, if I come up here and hook up this function generator, so what can I do if I've got DC? So this is the output of my function generator. And you got to mention, I'll show y'all, we'll look at audio before the end of the term. It's a composite AC, but it's really, really cool. So let's see, I got it on sine wave. So this is the output of this thing called a function generator. So Alabama Power, by the way, if you see this on the oscilloscope, it's telling you that your scope is going too slow. So what I'm going to do is I'm going to decrease the time for division, and then pretty soon I'll get the sine wave, right? Well, there's a sine wave. Now this is not coming from Alabama Power. This is coming out of this function generator. This is electronically generated. This thing plugs into Alabama Power running at 60 cycles per second at a certain voltage. Who controls that voltage? Huh? Alabama Power, or here TVA. But with this guy right here, I can come over and grab a knob and I can change the amplitude of that AC. I can come over and grab a knob and I can change the frequency of the AC. Now why can I do it? How does it make AC? Well, inside this thing, it's got a plus and minus supply. And if I've got a plus and minus supply, then I can use solid state devices to control that supply and generate what? I can control this AC. I can set the amplitude for it and I can set the frequency. Now, if you ever look at audio, the frequency is constantly changing because audio going to your speaker is a composite of all those different frequencies.
but they're going to go above the line and they're going to go below the line. It's AC. Well, how can your radio do that? Well, it's got to take, 12 volts DC and convert it over to a plus and minus DC, so we can do what? So we can control it. So that answers your question. So we use negative DC anytime we got audio. Anytime we got audio, we got to have plus and minus DC. I'm sorry. Anytime we got audio that we can control, right? And we got to control. So if I plug in a speaker to Alabama Power on this transformer right here, it would give me a tone, but it would always be what? 60 hertz. But we can't put DC on the speaker. Can't put DC on the speaker. It'd burn the speaker up. And that's usually what happens is one of your outputs will blow and you'll lose your negative power supply. And your positive power supply is there and your amp chips off. The people get out there and keep resetting and they burn their speakers up because they keep putting DC on that thing. So if your amplifier ever kicks its safety and you reset it and it kicks it again, don't keep doing it or you'll burn them big old expensive speakers you got up out there. We got an amp in here, by the way. I need to show y'all if I can find it. It's a Lansing that is flat burned up. So we'll look and see how we can get negative and positive here pretty soon. It's not too hard. Are we okay? Half-wave rectifiers, are we okay there? Everybody okay? Yes, no. So the regulator in the circuit that maintains an almost constant DC output voltage to the load and with varying input voltages and varying load currents. Regulators can consist of a single electronic device in the form of an integrated circuit or many discrete electronic devices. So we'll look at both of these. So you can buy voltage regulators. We can buy variable voltage regulators and we can buy fixed voltage regulators. And what we'll do is we'll take one of the trainers apart and we'll look in it and see the power supplies in the trainer. And we showed y'all this, and then we looked on half-wave. So the first full wave we're going to look at is we're going to call it we talked about rules of thumb, right? We talked about PIV. What's the PIV? The book uses the term PIV, but you're not going to see this term used in diode data sheets. They'll refer to this as the reverse breakover voltage. So the diode can only block so much voltage. If you exceed that voltage, and this is peak. Now I like this one because it's peak. So that means I've only got 5.9 volts out, but what does that diode have to block? That diode has to block 17.8 volts. It has to block peak. Y'all understand that? So this gets people a lot confused. They've got a power supply and it's a 10 volt output and they think they can buy a diode that's got a 10 it can block 10 volts and then it wipes it out because it's got to block what? Peak. Everybody understand that? So this is a good term because it makes peak inverse, which means the opposite, which would be a reverse bias, would be voltage. But when you look at the data sheets, you're not going to find PIV. They're going to call it what? The reverse breakover voltage. Everybody understand that? I think we looked at data sheets last class. So that's what they're showing there. We already did that. We looked at the negative half wave. Everybody okay? And then we get into our full wave rectifiers. What we're going to do with our full wave rectifiers is we're going to somehow take the other alternation that we're not using and we're going to steer it to the same. We're going to steer them to the same side. So if I've got a negative, if I got a
power supply, we're going to steer the negative up to the top. If we got a negative power supply, we're going to steer the positive down to the bottom. So what we're going to have to do is we're going to have more than one diode. You understand that? So the first one we're going to look at is we're going to look at what we refer to as a center tap. So this is full wave. Y'all understand? Yeah, I wouldn't take a break. Y'all understand? Are we okay? All right, I'll take a 10-minute break. Specification, setting up the VI characteristic curve for a diode. So we're not going to use an oscilloscope tonight. We'll use a meter. And we'll modify the program. Everybody got those lab books. We'll have to look and see how we're going to have to modify that circuit a little bit because of the range of our power supply. A full wave, this is the block for a full wave. So we get in a sine wave, but we're taking advantage of two alternations, or both alternations. Which means the output frequency is twice the input. So this is a cycle over here, which is one, this is a cycle over here. You understand that? So it means if I'm putting 60 hertz in, then I'm going to get 120 hertz out. You understand why? Okay? So half wave, the output frequency is the same as the input frequency. Full wave, the output frequency is twice the input frequency. Because this is that negative, this over here was the negative alternation, but somehow we steered it up here to the top, right? And we're going to do a diode with that. So, and this is not really important right now until we start adding trying to calculate our filters. How long the filter has to run the load, it depends on the frequency. So this is another advantage of a full wave rectifier. If I put the same capacitor in there, we get better filtering out of it because it don't have to run the load the entire time. So this is full wave. So here, if this is 15 volts peak, then what would be the output? Huh? How can we get, remember, what we're dealing with here is, this is DC, and DC is an average. So if it's got a 15 volt peak, you can't say we're going to get 15 volts out. Y'all understand? We're going to get the average of this. We're not going to get the peak of this. We're going to get the average of this. So this is an average. Y'all understand that? Yes or no? So the DC average of this, what would the DC average of this be? Well, a while ago it was half wave, and we lost one alternation. So this alternation right here would be DC average is 2V peak over pi, and then we average that with 0. That's why we use V peak over pi right over here. But here this is 2V peak over pi. This is 2V peak over pi. And what would be the average of 2V peak over pi? 2V peak over pi, right? You understand? Yes or no? So here the DC average is going to be equal to 2 times 15 divided by 3.14. Or you could say 15 divided by 3.14 times 2. That's the same formula, right? You understand that? So what would be my average output here? So automatically we get twice as much. It should make sense because 0 doesn't come into the average here, right? Well, it does, but it's part of 2V peak over pi. So what would be our output if I hook this up? What's that? 9.6 volts. We should have been twice of what we calculated for, right? Y'all understand why? Because last time we was averaging that 0, now we're not averaging that 0. So now we got a good feel. So everything's the same. All we got to do is on a half wave we use V peak over pi, right? Or 1/2 of 0.637. But I like to use V peak over pi for half wave and 2V peak over pi for full wave. Center tap, so we have two types. We have what we call a bridge. The book just calls this guy here a full wave power supply, but if you got your book, I want you to make a note that we're going to refer to this as a center tap, a full wave center tap or a center tap full wave. Either one is okay. Where's this at in the book? Somewhere in chapter 6, right? Or is it chapter 7? I think chapter 6 is power supply operation. That's right. So this is around rectifiers, talks about half-wave rectifiers, and then talks about full-wave rectifiers. And the circuit that we're looking at is on page page 132, and it's the one that they call full-wave rectifier. We're going to call that a center tap full-wave rectifier. And that way we can differentiate between the other. And of course, a transformer, we already talked about this. So what's the function of a transformer? Right. But what don't it change? Power. And this is what you got to understand, and people get all confused when they're running a load. So let's say I come over here and I'm on the primary side, and over here on the secondary side, I've got 10 volts, and I'm running it into a load that is using 10 amps. And this is a 2-to-1 transformer. So over here I'm creating 100 watts of power. Well, how much power are we getting in the primary? How much power is the primary delivering? It's the same. So my primary is delivering 100 watts of power. Y'all understand that? Because that's work. We're not changing work, right? You understand? What we're changing is what's current. Over here, this required 10 amps. Well, let's say this is a 2-to-1 transformer. Well, over here, this power, if this is 10 volts and it's a 2-to-1, then this over here is going to be 20 volts. But then I'd say, oh, what would I would be? I would be equal to P, which would be 100 over 20, which is going to be what? It's going to be 5 amps. So we have 5 amps in the primary because it's the high side, and we have 10 amps in the secondary because it's the low side, right? You understand that? And you said, wait, in Ohm's law it says if voltage goes up, current goes down. If voltage goes up, current goes up. But you're talking about over here on the load, we're talking about the source to the load. So yeah, if I was to double this 10 volts right here, this would go up. It would go up, right? You understand? But we're not doing that. What we're doing is we're playing around with the source. So if these were 100% transformers, when I flip this sucker on, TVA or Alabama Power would have to give me 100 watts because that's what we're paying for. We're paying for the work out here at the load, right? You understand? So transformers do not change power. They do a little bit. We call it the efficiency of the transformer. But for our purposes, we're going to assume they're 100% efficient. And one lab we used to do where we did this. We have two sides of a transformer. The one called the primary is the one pointing toward the source of the power. So all the primaries are pointing toward TVA here, right? You understand? And all the secondaries are pointing toward the load. We don't usually see the big substations out there. All we're going to see is just our transformer. By the way, big commercial transformers, don't call them. Most commercial transformers can be wired either step up or step down. So commercial transformers usually refer to the transformer as the high side and the low side. So the leads on the high side are going to be labeled with an H. It might be like H1, H2. And the low side, we're not going to use L because L we use for inductors. So the low side is going to be X, like X1 and X2. So that's the way the transformers, these are commercial transformers. You buy one from Radio Shack, they'll say primary and secondary. Step up reduces the AC voltage, but if it steps up, it reduces the AC voltage, but steps up increases AC voltage, but the current is lower than the primary, right? You understand? If we step it down, then the secondary current would be higher than the primary. But what sets the current? The load. So this is what we call this a center tap transformer. Don't pay any attention to the dots. It's on the top. Normally what happens on a transformer is wound. A lot of times what they'll do is they'll wound the transformers, they'll wind the windings right on top of each other. It is what we call an E-core transformer. Now what this causes to happen is that when this input's going positive, then if the current's going out here, the current it's going to be coming in there. So what would happen is over here, the actual secondary would be 180 degrees out of phase, which in power supplies makes no difference, right? Y'all understand that? So this is showing that the dots are showing that the polarity is the same, just for doing this, right? You understand? But in actuality, the secondary would probably be 180 degrees out of phase, because when the magnetic field's coming out of the primary, it's going into the secondary, right? And when it's going back this way into the primary, it's going the other way to the secondary, so they're always opposite. And we do have transformers, we call them pulse transformers that we use to fire SCRs. You got to get the polarity right, so they actually put the dots on there. So the dots would have the same polarity. So it's pretty nice. So that's all they're doing. And a lot of transformers are wound that way. It's just so convenient. They got a couple anyway, right? So they just wire them right on top of each other. And a lot of times you can see that. So the dot means we're going to use the same polarity on input and output. Now, so what we're doing is we're going to utilize, so a while ago I was not utilizing the center tap. So I could do a halfway rectifier without a center tap transformer. In fact, odds are that's what you're going to do. Because when they got to stick that other wire in there, it adds cost to the transformer. So center tap transformers cost more than untapped transformers. We're using center tap transformers because it serves all the power supplies that we need to make, right? You understand that? But we don't have to use it. Here, you have to use the center tap. You have to use it. So a center tap full wave rectifier requires a center tap transformer. So when you think about this, at this instant, and we'll use the polarities here. And of course, the amplitude of the polarity is constantly changing. But when we come over here, when the positive alternation starts up here at the top, then what would the center tap be relative to that positive? Well, that center tap is going to be negative relative to that positive, right? You'll understand. It's going to be at a lower potential. So if this is 12.6 volts, then this would be 6.3 volts less. Now, and this would be 6.3 volts less than that. So this would be positive, and this down here would be negative relative to the center tap. You'll understand that? Makes sense? So what happens, we can see right off the bat, this guy down here, I've got a negative on the anode, so this guy right here is turned off. Here I got a positive on the anode. So if I've got a positive on the anode, then the negative is coming back through here, right? You understand that? So this guy right here is turned on. That makes sense? And what's it going to do? It's going to allow the positive alternation to go through. That makes sense? Are we okay? Now, when this thing here swaps around, so eventually this is going to drop down. It's going to hit 0. When it hits 0, both diodes are turned off. By the way, the diode don't turn on until 0.7 of a volt, right? So this comes around here and does this, hits 0. Diodes turn off right around in there. That's why we lose that 0.7 of a volt. Then it comes over here when it goes down here. Then all of a sudden, this becomes positive, this is negative, and these guys right here swap, right? You understand? Yes or no? So what would happen to this guy right here? It's going to turn off. Now let's trace the current flow. Let's do the first one and trace the electron flow. So this guy's turned on. The electrons are going to leave this right here. They're going to flow out through here. They're going to flow up through the resistor, so that's going to make this side of the resistor negative. This side's going to be positive. It's going to come up. Why ain't it going to come back this way? Because this guy right here is turned what? Off. It acts like an open switch. This guy right here is turned what? On. It acts like an on switch. This guy is looking for the positive polarity that was created by that guy right there. So the diode's going to come up, it's going to go this way, it's going to go back to this side of the transformer. What's this side of the transformer doing? Nothing. It's turned off. No current flow in the other side of the transformer. Are we okay? So look at the polarity on the resistor. The bottom is what? Minus. The top is what? Plus. So what we see over here is we'd see this. Now, when this thing up here changes polarity, this is negative, which makes this positive in respect to that, which makes this negative in respect to that, right? Y'all understand that? So now, this guy up here is turned what? Off. This guy right here is turned on. I'm trying to use another color, so I can leave that one up. So let's use purple. So here's negative, here's positive. So this negative is looking for this positive. This negative is not looking for that negative, right? You understand? So it's going to come up here, flow out this, come over here, come up through here. This is going to be negative. This is going to be positive. Notice the polarity in the resistor is exactly the same. It's going to come up here and flow. Now, which way is it going to go here? It's not going to go up. It's going to do what? Go down, because it's looking for this positive and flow through this stuff. Come back to the transformer. Ready for the next. So what we get for this one is we get that guy right there. Now the problem is that we're only using 1/2 of the secondary at any one time. So it means that this is I've got a 12.6 volt center tap transformer up here. And this is the mistake everybody makes. Not everybody. Somebody in this class is going to do this. Somebody in this class is going to do that. So if it's a 12 volt center tap transformer, what we give you is we're giving you this entire voltage right here. We're giving you that 12.6 volts. But we're only using 1/2 of the transformer at a time. So that's all the way across here. So what is the voltage relative to the center tap? Well, the voltage relative to the center tap, this would be 6.3. This right here would be 6.3. So these peaks are going, this V peak out right here is going to be whatever that would come out to. Okay, so what would my output voltage be? What would I measure with my meter? We're going to do exactly the same thing, but we're just a little different. So first thing I need to do is calculate what? V peak, right? Now you can do this two ways. It don't make any difference to me which way you do it. We'll use the entire thing to start off with. So I'm going to come over here and I'm going to say V peak equals to 12.6 divided by 0.707. And what do we get? Okay, we're okay. Now, what do you think we need to do with that? Not yet. It's going to be half of that, yeah. So I would come up here and I would actually calculate BP, probably secondary, don't make any difference. I'm going to take 17.8 and I'm going to divide that by 2. Why are we going to divide that by 2? Because we're only using 1/2 at a time. And then that tells you B secondary time minus what? Minus 2. I mean, sorry, divided by 2. So what we got? Well, it's at 8.9. Then we do what? Then we calculate V peak out. Would be equal to 8.9 minus 0.7. Because these are silicon diodes. So V peak out would be equal to 7.1 volt, right? Then I calculate my DC out. So my volts DC would be equal to 2 V peak over pi. So we can take 7.3, we can divide it by pi, 7.1, I'm sorry, divided by pi, and then we'll multiply that answer times 2. So what we got? Oh, I'm sorry. I can't do math. I was looking at it a while ago. 8.2. Thank you, Scott. Of course, in the long run, that 100 millivolts is not going to make that much difference. But it's still a mistake. So what we got? $2.6 times 2. What? 5.2. Now you say, wait, Rich, that's what we calculated last time. Well, last time we was using the whole transformer. Right? You understand? We was using 12.6. The other way you can do it, and it's probably the best way to do it, is the first thing I would do is I would take the first thing I would do, I would calculate maybe V out, and then I would take 12.6, and then I would divide that by 2. And you get what? 6.3, and then take that down from there. So go ahead and divide the RMS by 2 right off the start off. And notice you'll come up with the same answer. And that way you might not forget about it. And this is the big mistake right here. Everybody's going to come up, somebody in this class is going to come up and give you 10.4 volts. And it's going to be wrong. If you show your work, there's a lot of stuff that's going to, if you show your work, it might be the only thing that's wrong, right? If you don't show your work, then there's going to be a lot of things. You understand what I'm saying? Because that's the very first step. So if I forget one of these steps, then if I don't show my work, then everything below that's going to be wrong. Are these diodes in parallel? This is another big mistake people make when they hook up. Are these diodes in parallel? They're not in series because they can't be in series, because if they were in series, they would be wired like this. And they're not wired like that because I got one in. Now you were right when you said no, but you gave me the wrong reason. They're not in parallel because the cathodes are connected together, but if they were in parallel, the anodes would be connected together. And what's between the anodes? Well, we got a dang transformer between the anodes, right? You understand that? So no, these are not in parallel. I'm going to come over there and somebody's going to have these suckers in parallel, even the class is small. But they're not in parallel, right? You understand? The cathodes are connected together, but the anodes are not. What's between the two anodes? Huh? What's between the two anodes? Here's this anode right here. Here's this anode right here. What's between the two anodes? Well, a transformer. The dang primary of the transformer. It gets me on motor controls. I go over there on motor controls. Every time in my motor controls class, I will draw a push button. And for some reason, people want to connect that to that. They see in there, well, you got to make a circuit. Well, the push button makes the circuit. And of course, I come up and I tell them, there's, what's between the front and what's in between the front bumper and the back bumper of your car? Are they connected together? You got a car in between there. So what's between the anodes? We got a transformer in there, right? But somebody in this class, it'd be surprised me. This is a small class. But it would surprise me if somebody don't do that. I would be pleasantly surprised. So here's the circuit. And as soon as we do this, this is a center tap transformer, and that's what this, so on the top of this transformer, it gives us the color code, yellow, blue, yellow. So blue is the center tap, and then my two outsides are here. The only one that makes a difference where you hook it up is that dang blue one right there. The yellows make no difference. You'll get the same thing out no matter which yellow you use. So where am I going to connect the center tap at? That's the important guy. Where does the center tap connect to? Huh? That is the ground symbol, but I've got a transformer. So this is probably one of the most, and you got to learn that because this is probably one of the most misused symbols in electronics is the ground symbol. You'll hear it even automotive people when they talk about the black lead of the battery. They said you need to connect that to ground. Of course, ground is what? It's a dang metal rod driven down in the ground somewhere and a copper wire running. Now the primary might be grounded. It's got the neutral. As soon as I go through that transformer isolates that. There is absolutely no neutral reference on the primary, on the secondary side of the transformer. So that's why they got that ground rod on your house. Because if they didn't do that, then what? When it goes to that transformer, it would lose that ground. Well, that's not true. They grounded it twice. They grounded at the transformer and they grounded at your house. So I determine what is neutral. Of course, here it doesn't make any difference. We get the same thing. It's just that normally what we do. So this right here technically should be drawn like this. That's the symbol for a common. And of course, ours is that. Now, why is mine grounded? Because of that little guy right there. So you got to be real careful, and this gets people in trouble. The black lead on your meter is a meter reference. Where can you put the black lead in your circuit? Anywhere. As soon as I connect that sucker up to any place in a circuit, that is ground. So if you hook it up into a grounded circuit and you stick this inside the circuit, then you've got a short circuit, right? You understand? So this is the right symbol. Why is it the right symbol? Because this is ground. So I've reestablished my ground. And we use transformers deliberately for isolation. Sometimes we don't want ground to come through. So let's see if this will focus in. Yeah, it focuses in real good. Notice, if we want something connected together, we connect it in the same vertical line. So you look here, the cathodes are connected together. Here's my blue lead. Where does my blue lead connect? Well, my blue lead is connected to the bottom of the resistor. The bottom on the schematic, right? You understand that? Okay. Here's my 2 yellow leads. Don't look at the blue up here, look up here. And then they're connected up here. The 2 cathodes are connected together. See, they're in the same vertical line. So I want the capacitor, I want the 2 cathodes connected together, and I want the resistor connected to the 2 cathodes. So they're in the same vertical line. When I look over here on my anodes, you notice they're in what? They're in different vertical lines. So they are not connected together. Now what do I have coming in here? Well, here's one yellow lead off my transformer. Here's the other yellow lead off my transformer, and I can swap those around. I can't move the ground or the common. Everybody understand that? Okay, so this is the positive power supply. If I make it a negative, I can't just swap one like I did a while ago. I got to swap both of them. Okay, you understand that? Everybody okay? People will come up and they'll connect the ground. They'll connect the common up in here. Now you got a short circuit because you would be shorting out the positive alternation of the transformer. Then you'd be shorting out the negative alternation of the transformer. So, a big problem we have in DC is people not understanding that resistors have 2 sides. And they say, well, that's got to connect to R1. And they say, well, there's R1 right there. And they connect it to R1, but they connect it to the wrong side. So it's very, very important that you understand components have multiple sides. And when you say connect it to R1, first thing you got to figure out is what? Which side? So on the schematic, I called it the bottom side, but over here in my drawing, it'd be the left side. So I got this resistor connected. I got this resistor connected to my center tap. Now remember, this is not inside the transformer. This is not inside the trainer. That is a symbol we use to replace a wire, right? You understand that? So the more symbols we can use, the less complicated the diagram's going to be. So that is a wire, and that happens to me all the time too. Well, I thought that says ground right there on the trainer. I thought the ground was inside the trainer. It is inside the trainer, but you gotta run that wire. Everybody understand that? So now our circuit's hooked up. So let's see if it's working. It's powered up too, guys. So here's my oscilloscope. I need to set it up so it don't blank. And here's so as soon as I hook up this red lead, this lead right here, then that is grounded now. So if I said, okay, I want to measure the voltage drop across those diodes, and then I come up here and I hook that sucker in right there, then I've got a short circuit. Because what I'm doing now, I'm taking this and connecting to that, right? You understand? So here's the way I got it. I got it across my load, and there's our waveform. A while ago, we don't have that flat spot anymore, do we? We get both alternations, positive DC. But it's still pulsating DC. Yeah, motors would love this. They don't care. Light bulbs would love this. LEDs would do a good real job of this. LEDs would be flashing. LEDs are extremely fast, but our eyes are not. So if I put an LED across this, it would look like it was on all the time. And we calculated, 5.2 volts. We know it's going to be high because we know the output of our transformer is high now. So we'll turn our meter back on. We just can't measure current with this meter right now. And I'm going to measure the current. I'm going to measure the voltage across the load. I'm going to put my meter across. I'm trying to get across the load. That's what I just did. Across the load, measuring what? DC. Dang it, Rich. Measuring DC, put it across the load. It's measuring 5.6 volts. So we missed it by 300 millivolts. Is that acceptable? Sure, because we use the ratings on everything in the circuit, right? You understand that? So between our calculated, we calculated 5.4, we're measuring what, 5.6? Good gracious. That's only 200 millivolts different. That's actually a little better than the halfway that we did. Well, we're still not quite there yet. Of course, if I come over here and put the capacitor across, got to honor the polarity, right, on the capacitor. And I'll show you a video, by the way. And all of a sudden now we got DC, but look how much cleaner it is. And that's the same size capacitor. It's still there, and we'll show y'all how to see that when we get here. There's still a what we call it a ripple voltage, but the problem is I can't see it. And if I come up here and turn it up so I can see it, my display goes off the top. So this is where we use this AC on the oscilloscope. Is we use this to block DC. So when you got it on the AC setting on the scope, it blocks DC. Any other time, we're going to use the direct couple. So that's what gets people confused because it says DC. And if I got my meter, if I measure DC, by George, I better put my meter on DC. And if I measure AC voltage, I better put my voltage on AC. On an oscilloscope, we leave it on DC 90% of the time. The only time we use AC is if we want to do what? Block DC. So I put it on AC. And now what I can do is I can turn this thing down and I can see that what we call the ripple voltage. There's my trigger. So that's exactly what's going on. So you can actually see the capacitor. We call it charging and discharging if you had AC. You can actually see it. This is not AC, but it's AC riding on DC, right? It's an AC component superimposed on DC. So if we want to look at the ripple, and we call it a ripple voltage. Did y'all see how I got that name? So we call that a ripple voltage. And what determines the amount of ripple? Well, the amount of ripple determines on the frequency of the pulses. And then, of course, the other thing that depends on is the size of the capacitor and the current required by the load. So we'll show you how to calculate that. So hopefully, by the time you got out here, you'll be able to build your own power supply. It was a lot easier when Radio Shack was around. You probably have to mail order your parts now. Are we okay? All right. So I got lab forms. Oh no. That's my liquid. Oh. I'm looking for the lab certificate. Okay. I did run them off. I'll read them off to you, and I'll find when I find them. I'll give them out. Oh goodness.